Hello everyone and welcome. This is the first video in my new lecture series and I'm really excited to start this journey with you. Over time I plan to add more and more lectures, so let's see how it all comes together. Now the question is that, who is this series for? Well, if you love mathematics just for the sake of it, say, then you are in the right place. But beyond that, my intention is to design these lessons to be especially useful for students preparing for math competitions, like for example the International Mathematical Olympiad. I'll be starting from the very basics of elementary number theory in these series of lectures, so you don't need anything advanced. Just basic arithmetic and high school algebra would be enough. More importantly, of course, what really matters is that you are curious and enjoy thinking about mathematics. If you have that, then you'll be able to follow along just fine. Now, here is how this series will be structured, or at least my intention is to structure them in this way. In each lecture, I'll introduce key concepts, definitions, and theorems, and most of the theorems will be accompanied by detailed proofs. I'll also go through examples starting with the simple ones and gradually increasing the level of difficulty of the examples. At the end of the lesson, of course not from this lesson, from the next lesson, I will give you a few exercises that using the material covered in that lesson and the previous lessons probably, you will be able in principle to solve those problems. So this is for exercises so that you can practice and increase your skills in problem solving. And in the next video I'll go over those problems in a tutorial session where I'll only focus on solutions, just like how you would have a practice session after a lecture at the university or even in high school. So this will be the pattern: one lecture followed by one or more tutorial sessions, then the next topic. Okay? Now if you're looking for even more of a challenge, I'm also planning, let us see how it goes, to create a separate playlist. Maybe something like Olympiad number theory or hard problems in number theory, something like that, where I'll cover really tough contest level problems, so you can follow these main lectures, practice with the exercises, and then push yourself even further with those more difficult problems. So that is the plan. I hope you find these lessons useful, and I am excited to get started. So let's dive in. Number theory. Number theory is one of the most fascinating and active branches of mathematics, even at research level. At its core, it's all about understanding the properties of integers. Numbers like 0, plus or minus 1, plus or minus 2, plus or minus 3, and etc. And of course, its famous subset, the set of natural numbers 1, 2, 3, 4, etc. Of course, that doesn't mean that we won't see any rational number or even real numbers along the way, but the main focus is always on exploring the structure and behavior and relation of integers, how they are related to one another. Okay? Okay, without further ado, let us start the lesson. In elementary number theory, the notion, the concept of divisibility is at the core. So, what is divisibility? Let us have a definition of divisibility here. So, let us say that a and b are integers. We say that b is divisible by a, and write this, we denote it by this symbol, a vertical line, and b, if there exists an integer q such that b is equal to aq. So a So b is divisible by a means there exists, you can somehow guarantee the existence of an integer q, so that if that integer q is multiplied by the number on the left, it gives you the number on the right. That is the relation. So in mathematical way, we can define it in this way. So b is divisible by a if and only if this symbol means there exists a q belonging to the set of integers such that b is equal to aq. If b is not divisible by a, of course we denote it by this symbol, putting a negation bar on this vertical line. So we read it as b is not divisible by a. Okay, now let us start with an immediate remark here. This symbol is read in the following forms. As I already mentioned, b is divisible by a. This is one way to read the symbol. We can also say that b is a multiple of a. So part A and part B, we bring B first and then A, which is a little bit unusual in mathematics. Formulas and relations are being read from left to right. So this is why we usually read it in this way. We say A divides B. So A divides B, which is this symbol, means B is divisible by A. Still, there are other ways to read this symbol. Is A is a factor of B, or sometimes we say that A is a divisor of B. But these two are more common ones, and most of the time I will use part C to read this symbol. Okay, now let us do this example. So according to the definition of divisibility, this statement is true. Either we say 15 is divisible by 3, or more commonly we say 3 divides 15. Why this is true? Because the number on the right, in this case 15, is equal to the number on the left, in this case 3, multiplied by an integer, in this case 5. So first of all, you see that this relation holds. 15 is indeed equal to 3 times 5. 15 is the number on the right, 3 is the number on the left, and this 5 is indeed an integer. So yes, this is true. For the same reason, part B is also true. Minus 4 divides 16, because the number on the right, 16, is equal to the number on the left, minus 4, multiplied by an integer. Coincidentally, it's again minus 4. So 12 divides 0 is also true, because the number on the right, 0, is equal to the number on the left, 12, multiplied by an integer, which in this case is 0. 0 is the only integer that fits this equation. Okay, but doesn't matter, because 0 is an integer, so this is also true. Importantly, this one is also true. So if someone tells you 0 divides 0, is it true or false? We say it is true, because the number on the right, in this case 0, is equal to the number on the left, in this case again 0, multiplied by any integer q. So you don't really need to fine-tune this k here. In the previous cases, q here is only 5. Here q is only minus 4, and here q is only 0. But here you have the freedom. You can choose q any number, but we don't need any number, we need integers, so q can be any integer number. Okay, to prove that a divides b, I need to guarantee the existence of only one q for which b is equal to a times q. But here I have infinitely many choices, even we can say it is better. So 0 divides 0 is a true statement. The reason I brought this up here, because I want to see that how we make our definitions might change our intuition. Because usually when it comes to this, people think as a fraction 15 over 3. When it comes to here, people think as fraction 16 minus 4, and they say that, okay, 3 divides 15 because the result of this is 5. 5 is an integer. Minus 4 divides 16 because the result of this fraction is minus 4, and minus 4 is an integer. And then even here you see that when you write 0 over 12, 0 over 12 is 0, and 0 is an integer. So you see the idea of writing this expression as a fraction, whose numerator is the right number and the denominator is the left number, and demanding that the result of the fraction is an integer, hope it works for the first three cases, but not for this case, because if you write 0 over 0, 0 over 0 is undefined, so you cannot say that 0 over 0 is an integer, okay? But because the definition was not, the definition of A divides B is not that B over A is an integer, okay? So I'm not using that, I'm using the definition that I presented here. So 0 divides 0 is indeed true. But what about this statement? 5 does not divide 22 is true. Why? Because if you say 5 divides 22, it means that the number on the right can be written as the number on the left multiplied by an integer q. But you know that the only number q that satisfies this relation is nothing except 22 over 5, which is not an integer. So even though I can find a number like q for which this relation holds, but that q is not an integer, so this means that 5 divides 22 is false, so it means its negation, which is this one, is true. This one is also true because 0 divides 3 is not correct, is not true. Why? Because if it is going to be true, it means that you can find an integer q so that the number on the right, 3 in this case, is equal to the number on the left, 0 in this case, multiplied by that q. But immediately you realize it is not possible because the number on the right is always 0 and the number on the left is not 0, so it cannot happen. So this means that this is false, so it means its negation is true. Okay, so as a remark, as we learned in the previous example, if a is an integer, then 0 divides a if and only if a is equal to 0. This IFF is very common in math text. It is not a misprint. Be careful about that. It's not a typo. So it means if and only if. So here, if I want to read it, I would read it as 0 divides a if and only if a is equal to 0, meaning that if someone tells me that 0 divides a, I can conclude that a is equal to 0, and if someone tells me that a is equal to 0, if I want to, I can conclude that 0 divides a. So that is the meaning of this phrase. So remember, if you see this and you are supposed to make it, if this statement is supposed to be true, there is only one scenario, and that is the number on the right should also be 0. And now here, if a is a non-zero integer and b is any integer, then a divides b, as you anticipated before, is that b over a is a fraction whose numerical value is an integer. Okay, so if you want to prove that, if you know already that a is non-zero, and you want to prove this for integers a and b, equivalently, you can set up the fraction whose numerator is the right side and the denominator is the left side and prove that this fraction is an integer. So that's an alternative way of proving that a divides b is indeed a true statement. Okay, let us do another example. Determine all natural numbers n such that 0 divides 2n squared minus 3n minus 2. Okay? Okay, we just learned that if this is going to be true, because the left-hand side is 0, this happens if and only if the right-hand side is also 0. So in other words, if I want to solve this, I have to answer this question for which natural number or numbers this is the case that this is 0. But this is very simple. I just use ABC formula, for example, to solve this quadratic equation. So n becomes 3 plus or minus a square root of minus 3 to power 2 is 9, and then minus 4 times this times that becomes plus 16, and then divided by 2 times the coefficient a, which in this case is 2, so 4. And then 9 plus 16, 25, so it becomes 3 plus or minus 5 divided by 4. Then I will have two options for this equation. Either I choose the positive sign, so it becomes 3 plus 5, 8 divided by 4, 2. And then I choose the negative sign, and is 3 minus 5 minus 2 divided by 4 minus a half. yes, but this one is not acceptable, yes, because it is not a natural number, and the only answer that we have for this problem is n equals to 2. Okay, very simple. Okay, another example. Let m and n be natural numbers. So show that m factorial times n factorial divides m plus n factorial. Okay. Okay, one way, we haven't reached to that level that solve this within the number theory itself, yes? If I want to solve this, we need more theorems. I mean, if I want to prove this relation only using the properties of integers, okay, we have to know more theorems in number theory, which still we don't have it, or I assume that we don't have it, because I want to respect all the prerequisites now. So I want to invoke one thing from combinatorics. So let me just mention that here. Let me change my color. So that's some kind of a recap. If I have a number n, which is a natural number, and if I have m is also a natural number, but I have a constraint, 1 is less than or equal to m is less than or equal to n. And let us say that I have n people. My goal is to choose m of them. In which order does not matter. Okay, I hope that you have studied a little bit at this level, combinatorics at least. So what you can do then, we have a binomial coefficient that you write it in this form: n choose m. This is the number of ways that I can choose m people out of n people if the order of how I choose them is irrelevant. And then we learned that in combinatorics that this number, if you want to calculate it, the answer will be n factorial, the top number factorial in the numerator, the bottom number factorial m factorial in the denominator, and the difference between them factorial again in the denominator. So that's the number of ways that I can choose m people out of n people. Okay? Now we just learned that, do you remember? We just learned that if a is not 0, of course, and b is both of them are integers. If a non-zero is an integer, b is an integer as well, instead of showing that a divides b, equivalently we can show that b over a is an integer. Yes. So here, instead of, we know that this is not 0 because m factorial is not 0. The minimum value of m factorial is 1, so this is not 0, and then this is an integer, that's also an integer. So in other words, actually they are natural numbers in this case. I want to prove that this is valid, so it means that I take this one and then divide it by that one and claim that this fraction is an integer. That's very simple now. Why? Because now let me choose the original color here. I take the number on the right and then divide it by the number on the left. And my claim is that this is an integer. But this can be immediately seen as a binomial coefficient whose top number is m plus n and the bottom number is m. Yes? But we know that this why this is true, because if I ask you to open this, using this formula, you will write this number on top according to the formula, which is correct. You write this number in the denominator, which is correct, and then the difference between them factorial, which is n factorial in the denominator. So this equality indeed holds. But this is the number of ways that I can choose m people out of m plus n people. Definitely this number is a natural number. And we are done. Yes, so I was able to show that if I divide the right hand side by the left hand side to make this fraction is a natural number. So this means the right hand side is divisible by the left hand side. As I told you before, we will be able to solve this problem only using number theory theorems, but we haven't reached to that level. But I just want you to do it right now here in this way. Okay. Okay, another theorem which is good to know: the product of n consecutive integers is always divisible by n factorial. Okay, so let us see why this is true. Okay, so let us say that, first of all, let us talk about n consecutive natural numbers. Instead of proving that n consecutive integers, the product of them is divisible by n factorial, let us concentrate on n consecutive natural numbers. Okay, so I would say that let the numbers that I have, let n be the first natural number. Here I am assuming that n is a natural number. The next natural number, of course, is n plus 1. The next natural number is n plus 2. So far I have written 3 of them, but I want to have n of them. So what I will do, I will continue this list. The last one, the number n1, is n plus n minus 1. Yes, because this is the first one, this is n plus 0. This is the second one, this is plus 1. This is the third one, this is plus 2. So this is the nth one. This means that this number should be 1 unit less n minus 1. Now my goal is to prove for you that if I multiply them, this number becomes divisible by n factorial. So let us do that. I want to multiply them. So what will I do? I will multiply this n by the next number, by the next number, and then I continue multiplying them until I reach to the last number. Okay, my claim is that this is divisible by n factorial. In other words, I want to show that if I divide this by n factorial, it becomes a natural number. This is my goal. Okay, how can I do that? I will rescale my fraction by this combination. I will multiply this by n minus 1, and then n minus 2, and then n minus 3, and then I continue until I reach to 3, to 2, to 1. So I multiply the numerator by this expression. To compensate for that, I have to divide by the same expression as well to make sure that I am not changing anything, yes? Okay, now let us see what happens. Now what do I have in the numerator when I multiply them? I have number 1 multiplied by the next one 2 multiplied by 3 up to n minus 1, then n plus 1, n plus 2 up to n plus n minus 1. So the numerator is nothing except the product of all natural numbers starting from 1 up to n plus n minus 1. So this becomes nothing except n plus n minus 1 factorial. Okay, what happens for the denominator? For the denominator, I have this one which I will copy and paste, but I will also have the green part. But what is the green part? The green part is the product of natural numbers starting from 1 up to n minus 1. Yes, one after the other. So this is nothing except n minus 1 factorial. Okay? But it is immediately clear that this is equal to the number of ways that I can choose n people out of n plus n minus 1 people. Yes? So why is that true? Because if I ask you to open it up, you will put this number factorial in the numerator, which is correct. Then you put this number factorial in the denominator, which is correct. Then you make the difference between them. This one and that one are gone, you get n minus 1, and then you put the factorial of that number in the denominator. That's correct. But binomial expansion, binomial factors, the number of ways that I can choose n people out of n plus 1 minus 1 people, n plus n minus 1 people, is exactly a natural number. So that's a natural number, so I am done. So this means that this expression that I had is equal to this expression, and this is a natural number. Of course, here I have assumed that my n is a natural number, but it doesn't matter. If you assume that n is an integer, might be n is negative. Okay, so what happens? Then it means that in this product, either all of the numbers will be negative, or some of them will be negative and some of them will be positive. So then that product either becomes exactly equal to this product, depending if you have even number of minus signs, or it becomes the minus of the product of this expression if the number of minus signs encountered in your problem is an odd number of minus signs. So, and then that doesn't matter, yes? The existence of a minus sign will not change the idea of divisibility. So this is why this is always true, okay? Okay, another example. So let n be an integer. We want to show that whatever n is, 6 always divides n times n squared minus 1. In other words, no matter what you choose for n, as far as n is an integer, this product is always divisible by 6. So let us see why this is the case. Okay, this is very easy if you use that theorem. Of course, there are other ways to prove this. We will learn a lot of these techniques later. But here we can immediately solve the problem using the theorem we just learned about the product of n consecutive integers is divisible by n factorial. Why this is useful here? Because n times n squared minus 1 using conjugate rule can be factorized as n times n minus 1 times n plus 1. But I can rearrange this as n minus 1 multiplied by n multiplied by n plus 1. Now look, n is an integer. If I ask you what do you have here, you will tell me that I have the product of 3 consecutive integers, because this is the first integer. If I ask you what is the next integer, you add 1 unit to it, it gives you n. If I ask you what is the next integer, you will add 1 unit to it, it gives me n plus 1. So this is the product of 3 consecutive integers. According to the theorem we just learned, is divisible by 3 factorial. But what is 3 factorial? 3 factorial is 1 times 2 times 3, which is 6. So this expression is indeed divisible by 6. Yes? Okay, the next theorem is also a very simple theorem but handy. If a is an integer and m and n are natural numbers so that m is less than or equal to n, then we have these relations always holding. So I am tabulating them, itemize them as a theorem because I will use them extensively later without feeling that I have to prove them every time that I'm going to use them. So every number divides itself, including 0, because I told you that 0 divides 0 is also a true statement in the way that I defined divisibility. Okay, I will not prove all of them because they are very simple. So every number divides itself. Every number divides 0. In other words, 0 is divisible by every number, even if that number is 0, because again, 0 divides 0 is true. This means that every number is divisible by 1. Every number is divisible by minus 1. These are very obvious ones that you can prove easily. And then a to power m, what is m? M is a natural number, a smaller one. N is the natural number, the greater one. So between m and n, m is the smaller one. A to power m definitely divides a to power n. That m and n has to be natural numbers, not integers, is very clear, because when you say integers, it means that it is possible that m and n might be negative numbers. And then if m is a negative number, say let us a to the power of minus 2, a to the power of minus 2 is a to power 2. And this symbol does not make sense unless what is on the left and what is on the right are integers. If they are not integers, we cannot talk about divisibility. Okay, divisibility is something defined only in the realm of integers. Okay, so for example, let us have a proof for this one. Okay, so here what I have, I know that m is less than or equal to n, My goal is to show that a to power m divides a to power n. Okay, so what I will do, I would say that a to power n, the number on the right, is equal to a to power m times a to power n minus m. This we know, okay? But now what is happening here, this is the number on the right. This is the number on the left, yes? And this is definitely an integer. Why is that? Because a was already an integer. N and m are natural numbers so that n is greater than or equal to m. So n minus m is definitely an integer. A non-negative integer. So this means that I am quite sure that this number, whatever it is, belongs to z. So now you see what is happening. The number on the right here is equal to the number on the left here, multiplied by an integer. So this is true. Very simple. Okay, another theorem is let a be an integer. A divides 1 if and only if either a is minus 1 or a is equal to 1. It's very simple. So it means that if 1 is divisible by a, then there are two possibilities. Either a is minus 1 or a is equal to 1. This symbol in mathematical logic is a red or. And this one is and. So this is and this one is or. Okay? Okay, I think the proof is very simple, but this is very handy. So whenever you see this, you can conclude either a is minus 1 or a is equal to 1. I will leave the proof to yourself, okay, so you can do it very easily. Okay, so that theorem is a special case of, for example, an example of this type. So here, determine all natural numbers n so that this combination 2n plus 3 divides minus 7. So in other words, this number should be a factor of minus 7. Yes? But what are the factors of minus 7? So this means that 2n plus 3, I have some scenarios. Either it is minus 1, or it is 1, or it is minus 7, or finally 7. I do not have other options because, as we will see later, 7 is a prime number, of course, you know that. So these are the options that I have. From the first one, what happens? N becomes what? You can do it in your head. Equate this with this one in your head. So 2n becomes minus 4 if I move 3 to the other side, so n becomes minus 2. Or what happens if I put it equal to 1? I move 3 to the other side, so 2n becomes minus 2, n becomes minus 1. Or this one, I move 3 to the other side, it becomes minus 10. So 2n is minus 10, n becomes minus 5. Or finally, what happens? If I put this one equal to 7, 2n becomes 4, n becomes 2. But because they have mentioned in the problem, find all natural numbers, this is not acceptable, this is not acceptable, this is not acceptable. The only acceptable one is n equals to 2. Okay, another handy theorem, these are simple. You know, if I know that a divides b, if I want to, I can multiply the right-hand side by a minus sign without multiplying the left-hand side. If this is true, this is still true. If I want to, I can multiply only the left-hand side by a minus sign without having to multiply the right-hand side by a minus sign as well. That is, if this is true, that is also true. Or if I want to, I can multiply both sides by a minus sign. This is still true. If I want to give you a comparison in inequality, if I know that a equals to b, I am not allowed to conclude that minus a is equal to b. I am only allowed, if I want to multiply one side by a minus sign, I have to multiply the other side by a minus sign if I insist to keep the equality intact. But if it comes to divisibility, relation is less strict than the equality restriction. Yes, so that is what I want you to know. If you have this, you're allowed to multiply only one side, or if you want, you can multiply both sides. If the first one is true, all of these will remain true. The proof is so simple that, again, I want to leave it as an exercise for you. But please do them. If you're a little bit dubious about your skills in this area, do them, unless you really are confident that you can do it. Okay. Another important theorem is that if a is an integer and b is a non-zero integer, and we know that A divides B, then absolute value of the number on the left, A, is less than or equal to the absolute value of the number on the right, B. Okay, so in other words, if B is divisible by A, the absolute value of B should be greater than or equal to the absolute value of A. Of course, if B is not equal to 0, because you know that if B is equal to 0, A can be any integer. For example, 5 divides 0 is a true statement, but absolute value of 5 is of course not less than the absolute value of 0. So this is crucial. If B is 0, this is no longer guaranteed. But if B is not 0 and this is true, then this is guaranteed. So let us look at the proof of this one, okay? Okay, so here we know that A divides B. So what is the meaning of this? This means that there exists a Q in Z such that the number on the right, B, is equal to the number on the left, A, multiplied by that Q. Okay, this is what I get from this assumption. But there is one more assumption, that B is not equal to 0. So this means that Q, even though is an integer, it cannot be equal to 0. Yes? So Q is not equal to 0. Why? Because if this Q is 0, then it means B is equal to 0, but B is not equal to 0 according to the assumption. So this means that based on this condition and this condition together, you can conclude that there is a non-zero integer Q, so that B equals to A times Q. Yes? Okay, now if that is the case, this means that absolute value of B is equal to absolute value of AQ, but absolute value of B becomes, we know that the product, if I want to take the absolute value of a product, I can write it as the absolute value of the first one and absolute value of the second one. Okay, that's a property of absolute value. Okay, and then we know that Q is an integer, and we know that Q is not equal to 0. So then it means that the absolute value of this Q is at least 1, is 1 or greater than 1. So then this means that if I multiply everything by absolute value of A, which is a non-negative number, this becomes greater than or equal to absolute value of A. But now look, what is this expression? This expression is nothing except absolute value of B. So here I would write absolute value of B greater than or equal to absolute value of A, which means exactly as what I need to prove. Okay, this is also a very important remark. We will use it a lot. According to the previous theorem, if someone tells you that A divides B and B divides A, then A is either minus B or equal to B. Okay, but in this case I have to be a little bit careful. I have to write A and B are non-zero integers. Okay, so that was a little bit mistake from my side. We have to mention that if A and B are non-zero integers. Okay, please fix it yourself. And if I know that A divides B and B divides A, then I can conclude that there are two possibilities. Either they are equal or they are opposite to one another. Of course, in particular, if someone tells me that A and B are natural numbers and they guarantee that A divides B and simultaneously B divides A, then this is the only thing that I can conclude that, okay, these two numbers are equal. Okay, let us discuss a little bit about this. Okay, so if A divides B, if B is non-zero, we can conclude that absolute value of A is less than or equal to the absolute value of B according to the theorem we had. And if I know that B divides A, if A is non-zero, then it means the absolute value of B is less than or equal to absolute value of A. But these two things simultaneously happening means they have to be the same. And if the absolute value of two numbers are the same, then it means that these are either equal or negative of one another. So it means that A is either plus B or minus B. But if they have mentioned that A and B are natural numbers, so this means that both A and B are positive. So this means that A equals to minus B cannot happen. So the only option left for us is that A is equal to B. Okay? Okay, so as I told you before, my goal is to make exercises for you starting from the next lesson. So in the next lesson will be much more exciting and much more interesting. But if you want to start something in mathematics from scratch, might be the first few lectures seems a little bit boring. But if you keep your patience, I hope things becomes more exciting for you. Anyway, I hope that this video was useful for you. Please write your comments if you have any suggestions how we can improve these lectures. What is your objections? What do you think I can do to make it better? Until the next video, be safe and goodbye. Thank you.